homework assignment, which you've got now. Let's begin by looking at these announcements. First of all, homework 1, which you've got in your hands, that's due a week from today. Well, I've got the time wrong though. Upload it to Blackboard before class. So you've got until noon, and that's due on Wednesday the 19th. So that deadline is programmed into Blackboard. And all of the tentative assignment due dates are in the course schedule that I've given you. And so you can kind of tentatively see what your timing is going to be of upcoming assignments. And you'll note on that schedule that the environmental engineering graduate students, the due date for their project submissions is indicated as well on the course schedule. Any announcement related questions that you might have before we continue talking about flumes?
For this class, do you upload your notes like you did in all your other courses?
Yeah, the PDF file of the notes are available on Blackboard right now. And so you can print it out with 2 slides per page, 3 slides per page, and so on. So I've just loaded those this morning. Are there other questions? Okay, so where we left off was we were talking about flumes. This is a side view of a flume, and remember, the reason why we like these is to measure flow. And what's advantageous about a flume for measuring flow is that it's relatively simple to just measure the depth at 2 locations. And there are calibrated empirical equations that can relate the flow rate that's going through the flume to the depth. And you'll see that each one of these, it's the depth at the upstream location, H sub A. The reason why we measure the downstream depth is to check submergence, to see if the hydraulic jump is free-flowing or if it's submerged. And so if it's a submerged hydraulic jump, we have to apply a correction factor. If it's free-flowing, then we can just substitute it directly into one of these equations. So for to check the submergence, then the downstream depth, H sub B, is compared to the upstream depth. And what we classify as submerged would be above the ratios that are indicated here. And so if the downstream depth is more than, let's say, 60% of the upstream depth for a flume that's 22.9 centimeters wide, then we'd consider that submerged. And once you determine if it's submerged or not, so if the H sub B is less, the downstream depth is less, then that means the hydraulic jump is flowing unencumbered, and you can just use these equations with no correction. But if you do need to correct, then what you'd do is you'd find the appropriate figure. This one, C, is for 0.3 meters. And then you'd start with the upper head depth, intercept the percent submergence curve, and then you'd come down and read the correction. And so if we were doing the problem for a 0.3 meter wide flume, then I just subtract the correction from the flow rate that I'd calculated with this equation. If it is a flume of any other width, then for me to use this figure, I would have to then multiply by a correction factor on top of the correction that I look up. So delta Q is how much below the free flow capacity the flume is. And so it's going to be the free flow capacity minus delta Q. And you find out delta Q from the horizontal axis of this figure multiplied by the applicable correction factor. So let's practice this with this equation. So we have a flume with a throat width of 0.61. That's the W. And so 0.61 throat width, you can see here in this list of equations, the range of flow rates, the range of throat widths is what guides which equation you're going to use. So for 0.61, it's the second to the bottom equation that I use. So you can see Q is a function of the width, the H sub A, and then I've got a pretty complicated exponent here as well. An exponent on top of an exponent. So this is a tricky empirical equation. And what we usually see for flumes of this throat width would be a free flow capacity up to 4 cubic meters per second. That's just to give you an idea of what could be accommodated for a flume of this width. Okay, so this is our base equation. And so the first thing we would need to do in this example is check the submergence. And so the upstream depth, H sub A, in the converging section is 45 centimeters. The depth in the throat is 39. And so we need to have this check of H sub B divided by H sub A. So for this, H sub B is 0.39, 0.39 meters. H sub A is 0.45 meters. And so then the ratio, H sub B divided by H sub A, is 0.867. So the limit for this, for free flow, in this width range that we're in, is 70% submergence. What we have is 86% submergence. So it's not, unfortunately, going to be free flow. We'll have to calculate the free flow capacity, but then we are going to subtract out the delta Q. Okay, so here's the formula that we use for the free flow capacity. So the Q free flow is going to be 0.372 times the width, and I'll just make that substitution now. You see the equation we're substituting into on the screen. So the width of the flume is 0.61 meters, and then we have 3.281 times the H sub A depth, so that's 0.45 meters. And then we have an exponent of 1.570 times, again, the flume width, 0.61 meters. And then that flume width is to the power of 0.026. Okay, so it's best to do this in steps, not try to do all of the calculations in one single big equation on the calculator. And so what I do is I combine a couple of things at a time. So for instance, these first two terms multiplied together leaves us with 0.22692. And then we've got what's inside of the brackets here, the 3.28 times 0.45. So that is 1.47645. And then in the exponent, we've got 1.570 times 0.9872. The 0.9872 is what we get when we have 0.61 to the power of 0.026. Okay, so then if I do all of that, then what I'm going to end up with is that the free flow capacity is 0.4151 cubic meters per second. Let me just bring up my calculations onto the screen so that we get that recorded into all right. So how much we can accommodate through the flume is going to be less than this, because the fact that the hydraulic jump downstream is being drowned reduces the capacity. So it's going to be this, the actual flow, so Q actual will be Q free minus delta Q. So now we have to determine what is this delta Q. Okay, now the way that we do that, you can see that I've already put in a horizontal line and a vertical line. So the horizontal line is intercepting this left vertical axis where the H sub A is 0.45. This is a logarithmic axis. And so it's a little bit tricky to know exactly where to put that horizontal line, but it's further up than you might expect because it's logarithmic. And just to illustrate that, look at how point 2 is more than halfway between point 1 and point 3. Do you notice that? How it's not like right in the middle? It's because it's a logarithmic axis. And so if I'm going for 0.45, the point is it just needs to be a little bit higher than you might otherwise expect. So we go here for the intercept with the vertical axis, and then over to the percent submergence, 86.7. And so these curves are a little bit tricky. Here's the 70% curve, the 72% curve, and so what I want to intercept, this is the 86% curve, and this is the 88. And I should be between them, 86.7, a little bit to the right, and then down. So what I read off of this correction factor, like my view of what that correction ought to be, so Q corrected is 0.044 cubic meters per second. And remember, down here, the delta Q is the correction from this multiplied by a correction factor. And the correction factor depends on the width of your throat in the flume, so 1.8. So if I had a separate figure for my 0.61 meter throat flume, then I wouldn't have to apply the correction factor. But I've just got this 1, which corresponds to a throat width of 0.3. So the actual reduction in flow capacity is going to be even more severe than suggested by this chart. So that's why I'm multiplying by this factor of 1.8. 1.8. So the delta Q is 792 cubic meters per second. And that means that the actual capacity at the conditions that are described is 0.3359 cubic meters per second. Now, I've reported that to 4 digits, but that's not really realistic. You know, when you're eyeballing an intercept off of both the vertical and the horizontal axis, there's going to be a little bit of uncertainty there. So maybe what I ought to say is it's 0.34 cubic meters per second. You know, because I can't report to the nearest 10,000th of a cubic meter per second. But it's giving us, in most cases, enough precision to do the rest of the work that you'd need. You know, like if you were a farmer trying to irrigate a field and you wanted to know how much water had gotten out onto the field, you'd make a measurement with this flume, multiply it by how long you irrigated, and then that would give you the volume of water that had gotten out. Any questions about the specific calculations on this illustration? So you'll get some practice. In the homework assignment I've given you, in the handout here, you'll see that the first problem is a problem having to do with a flume. In fact, the second one is as well. The first one is just pure analysis. The second problem, you're having to not do design, you're having to do selection. You're trying to figure out which flume would be appropriate and what are going to be the conditions under a couple of characteristics that are described. So you'll get 2 problems having to do with the flume. All right, well, let's talk about culverts now. You see a lot of culverts in West Virginia because every road has a creek that runs next to it, it seems like. Maybe not every road. Every rural road does, though. Here in the urban areas of Huntington, they usually put that water underground, and so we see just the inlets to storm sewers, but it's not as visible as a ditch that's next to a road. So the purpose of a culvert is to pass water under the road, where the road wants to go straight maybe, but the stream is meandering and curves naturally to go under the road. And so the job of a hydraulic engineer is to size a culvert, and it's very closely related to the analysis that's done by a hydrologist. And so we're going to learn both. You're going to, later in the semester, learn how to determine what would be the flow rate that's going to pass through this pipe. And right now, we're going to spend a little bit of time learning how to analyze and design the size of a culvert that's required once you know the flow rate that's going to be passed through it. So how much water can get through that pipe obviously depends on the diameter of it, or the flow area. It depends on other characteristics like the length of the culvert, how steep it is, what it's made out of. And then also, it depends on what's happening in the stream that's after the culvert. And so if the stream after the culvert is very flat and shallow, and it's constantly backing up into the culvert, then it's possible the culvert may not be able to carry as much water as it would if the conditions downstream had higher conveyance. Here is a picture of a culvert in Mercer County. Someone who is doing a summer internship with DOH sent me this picture. I think that this is maybe just a temporary setup that was in place while they were constructing a bridge. The problem, as you can see, is the accumulation of debris upstream of that culvert. There's lots of branches and trash that gets thrown into creeks and rivers. And if it's smaller than the diameter of that barrel, it can get lodged upstream, and it could create a damming effect, and it may need to flow over the top. That's something that we're going to talk about today when we get into the HY-8 program, is overtopping. It's just such an apt term for what happens. Think about if there was really a lot of water. If there was so much water that these pipes couldn't carry it, what happens is the water goes over the top. Some of the water will continue to go through the barrels, and the rest of it will go over the top. And so in this situation, I don't know, but I would hope that it's paved along the top, because if the flow goes over the top and it's just gravel, it's going to wash all that gravel away, and then it's probably going to take the barrels with it. But my guess is that probably it is concrete or asphalt, because it looks like they've got a concrete face on the front of those where the barrels are embedded. When you are calculating how much water can get through here, you need to know the diameter of each barrel, the slope. You need to know how high the water is above the center of the barrel. So you'll be doing analyses to say, well, when the water level is a certain depth, how much water is getting through these pipes? And then you may ask yourself, if the water is at a depth that's greater than this, the elevation of the road, how much of the water will go over the road and how much it will go through the pipes? That's another thing that we'll look at today with HY-8. So this is here in West Virginia. Here's a picture. This is another view. Oh, it is. It's paved. That's great. This is going to last a lot longer if it's paved. They're all set for overtopping. If they went to all this trouble, maybe it's permanent, you know. I thought I remembered the students saying that this was temporary while a bridge was going in, but
a lot of those are actually really common, like up around the northern panhandle and stuff, because like those creeks flood so often. Yeah. They're just low water bridges. Yeah, you probably can't go over that a couple times a year when the creek gets too high. Here's one in Colorado. Same thing, multi-barrel culvert. This one's a little bit more steep, and I guess nothing really to say about that other than, I know. The invert is the bottom of this pipe. You can see that the water plunges into the stream, that the bottom of the pipe isn't at the same elevation as the bottom of the stream. So that's something that when we get into HY-8, you have to pay careful attention to, is the geometry of where everything is. You're telling the program the diameter of the pipe, how long the pipe is, but you're also telling it, for example, what is the elevation of the bottom of this compared to the elevation of the river that's downstream. Sometimes you just set the pipe right on the bottom of the river and build up around it. Let's go back to this other picture. I think that's what this is, where the stream itself is the same elevation as the bottom of the pipe. So the invert of the tailwater channel and the invert of the pipe are equal to each other. But here that's not the case.
Here's a concrete box culvert. There's a lot of different shapes and sizes of culverts. There's a culvert very similar to this in Huntington that passes Four Pole Creek into the Ohio River. It's kind of over by, not far from Ritter Park. There's some ball fields in the immediate vicinity if you know Huntington area very well. Sometimes it's just as simple as a corrugated metal pipe that's been buried, and these pipes are kind of meant to flex a little bit. They get their strength from the fact that the soil compacts in the haunches below that curve, and so you'd think that it would crush, but you could have hundreds of feet of soil and rock above the culvert, and the forces just kind of pass through and around the culvert and don't crush the pipe in a way that you might expect, because as it deflects, it gets additional strength. So a culvert is just a conveyance shape that allows water to flow under the road. And they're used because it's cheaper than building a bridge. Bridges are expensive, culverts are cheap. And they're usually used in different situations as well, for lower flow rates, or in a case where we don't necessarily care if occasionally the road isn't accessible, like that one in Mercer County we were just looking at. Maybe it's okay if a few times a year that culvert is submerged for a couple of hours. Maybe that's an acceptable rate of failure. So the way that we size them is a hydrologic analysis is done to find out the flow rate Q, and then once you know the flow rate and you know what your design standard is, let's say, for example, that you want your culvert to only fail once every 25 years. So you would do this hydrologic analysis and you'd find out the 25-year flow rate. Then you start to just try a bunch of different shapes and sizes and see how big does it need to be in order to get the water through without overtopping, for instance. So there are a variety of combinations of how high the water level is upstream versus downstream that dictate which formulas get used to find the capacity. So just like we were looking at, there's different formulas for flumes, there's also a lot of different equations for culverts depending on what the water looks like upstream and downstream. There's also a lot of different culvert equations depending on whether the pipe has shapes on the end of it to guide and kind of prevent scour. Head walls like this and wing walls are in part to make sure that the soil is stable behind it, but it also funnels the flow into the pipe. And so it improves the hydraulic capacity on this one in the right compared to if it was just a projecting barrel. There's more turbulence and more energy loss at the inlet. So there's a lot of different options in HY-8 where if you know that you have, for example, the end mitered, meaning that the pipe is cut at an angle to conform to the slope, it can account for the hydraulic effects of that and the improvement in energy loss compared to if it's just a simple projecting barrel. We'll maybe come back to this video. I don't want us to spend so much time watching videos that we don't get into the program today. If culverts are too small, then the water level will rise to an unacceptable height upstream of the culvert. So here's a picture of a road where upstream, which is over here, the water level got so high that water started seeping around the outside of the culvert. It was seeping through the soil. And it caused something called piping, which is where the small grain particles of soil get pushed out, and then the water starts to flow a little bit faster and faster until finally soil around the outside of the culvert has been scoured, and it causes a lot of damage. You can see that this road is closed for a good long time, and it's in part because the culvert that was supposed to carry this water was undersized, and there was too much head wall pressure pushing the water around the soil rather than through the culvert. So inlet control is when the limiting factor for how much flow can get through the pipe is the opening of the diameter upstream in the culvert. So here's just a few different illustrations of, depending on if the hot headwater is not submerging the inlet or versus is submerging the inlet. There's also outlet control, where you can see in each one of these cases the inlet of the pipe is completely submerged, and then it's more of the characteristics of the pipe and what the water downstream of the culvert is doing that determines what the flow rate is. In the old days, rather than using a program like HY-8, there were just books and books of equations that had been built into nomographs, where you would draw a line between 2 points and find the intercept. So if you knew the diameter of your culvert was 42 inches, and you knew, for example, what was going to be the headwater depth, so you'd go here, then you'd find the intercept, and that would allow you to predict what the discharge is. Or if you knew these two, then you could find what is the resulting headwater depth. And so they were carefully calibrated plots of data that kind of in the background was doing the calculations for you. But we have more flexibility than that now with HY-8. Here's just some pictures of culverts. I took these photos when I lived over in Dubai, and it's just another illustration that even in very arid regions, stormwater is a huge issue. And these, just to give you a sense of how big these culverts are, this is a picture of me and one of my colleagues. And so it was probably, I think, 12 feet tall arch culvert, and there was 2 of them. And so they're carrying a lot of water. And you can see they've armored the face of the side slopes there so that it doesn't get scoured away. See how they've got chain link and rock? Because they expect that it's very possible there could be overtopping. In addition to the flow through that barrel, it could be going over the road, and they don't want this to get scoured. So this is kind of like a permanent solution for water flow under that road. Here's a less sophisticated and fancy culvert where you can see that their solution to avoiding scour is old road signs, and it's in bad shape. It probably is going to undermine the structural integrity of this road. You can see cracks are already starting to form in the asphalt. But not everybody has the same budgets for roads as Dubai does. That's for sure. All right, so raise your hand if you've already downloaded HY-8. Good. Good. So we're going to spend some time going through that today. It's a new version compared to when I used it last, but I took a look before class, and it seems like the core functionality remains the same. They've just added a few new features that probably only apply to a very small handful of the people that are using HY-8. To get a feel for how it works, we're going to look at this example. Try and visualize. I've got 2 different views of this. We're starting with the top view. So I think you probably already have the idea that the road is this, and the creek is in blue. So you can see the red arrow indicates that the water is flowing from the left towards the right. And you can see that the width of the creek is 5 meters. And we're going to assume that it's a rectangular channel. And what I mean by that is, I guess I don't have a front view. Let me do a front view here on the whiteboard. All right, so we're going to have a pipe, and here's the road that's going over the top. So here's the road, the pipe you can see. And so the width, if the water was going to be overtopping, it would be flowing over a 5-meter width. That would be the crest length, as it's called, if this was acting as a weir. And so we want to analyze a certain diameter. We're going to see like what happens when we put, for a flow rate of 25 cubic meters per second, can we get that 25 cubic meters per second through a pipe that is 600 millimeters in diameter? So for D equals 600 millimeters, what I want to know is, where's the water level going to be at? Is the water level going to be up here, which that's okay. If the water level doesn't quite go over the road, that's fine. But if it does go over the road, then that means people shouldn't be driving over it. It means that there could be damage to the roadway surface. And so for a variety of reasons, what I want to see is how big does the pipe need to be to make sure that overtopping does not occur. Okay, so from this other view, we get some of the other information. So we get elevations. The invert of the pipe is at 300 meters upstream, and downstream, the invert of the pipe is 299.95. Okay, so those are the elevations. And you can see here, it's giving us station numbers. That's what's going to define the length of the pipe. You can see that the pipe is 20 meters long because the inlet is stationed at 1 plus 0, 0. The outlet is stationed at 1 plus 2, 0. So it's 20 meters long. Here's an elevation difference. And so the program is going to calculate the slope of the pipe from that. Also, we're going to assume that the stream after the culvert it matches up, that the elevation of the stream. Remember those pictures from the culverts in Colorado where the pipe was above the bottom of the stream downstream? Here they match. And so we're going to use these elevations when we start translating it into the computer. So the question is, can a 600 millimeter diameter culvert accommodate this flow with no overtopping? So the water level shouldn't rise to 307, because as soon as it gets to 307, the water starts going over the top of the road. So does everybody feel like they understand kind of the background and can mentally visualize the scene? All right, so if you've got it, hopefully you do, start up HY-8. Did I install it here or did I just download it so far? Luckily, it installs fast. It's sometimes amazing, the software that you can get for free. The reason why it's free is Federal Highways had it developed on contract, and any software that the U.S. government makes is generally freely available, whether it's the Army Corps of Engineers or Federal Highways or the Bureau of Reclamation. I guess maybe the exception to that would probably be like the Pentagon or CIA. I don't think they make their software available. All right, so now I think it's installed. There it is. All right, so follow along. We don't need to register. That's fine. Okay, so when you first bring up the program, the opening dialog is you want to create a new project and add a crossing. So that sounds good to me. Okay. But we already have a problem. If you look at the units, it says CFS. So we need to cancel this and change the project to metric units. So over here in the drop-down box at the top, I'm going to change it from US customary over to SI. Okay. Now I need to add a culvert because there isn't one any longer. And so I'm going to do culvert, new culvert crossing, and now you'll notice that the units are in CMS, cubic meters per second. Okay, so far so good. Any questions on how to change the units? Do I need to show that again? Are we all good for now?
Can you show the units again? I'm sorry.
Uh-huh. So just when you start the program, it'll automatically ask if you want to start a new project, and you cancel that. And then it's here in this drop-down box where it was originally in US customary, and we want to switch you over to SI. Okay. And once you've done that, it's culvert new. Okay, you could name the crossing if you want. Sometimes in a single file, you may have a river at multiple locations, different culverts for the same river. Here, we're just going to have one culvert at a single crossing, so you don't necessarily have to change the name. But let's begin just top to bottom, putting in data that we know. We want to analyze this starting at 0 cubic meters per second. The design flow is 25 cubic meters per second, and the maximum flow is 30. So we've just added the flow rate so far. Okay. This example mentions it's a rectangular channel downstream. So after the water gets out of the culvert, you know, is it, most of the time in a natural channel, it would be trapezoidal. But just for simplicity, we're going to assume that this one is rectangular. So we're going to leave it, the default is rectangular. Okay, so the bottom width, that's how wide is the river, 5 meters. Channel slope, it says here that the slope of the channel, S naught, is 0.0025. So that's 0.25%. So 0.0025 is the channel slope. The N value, Manning's N, that's talking about how rough is the material in the stream. So the N value is 0.05. That would be a typical N if you had like rock and gravel in the stream at the bottom. So 0.05 is what I'm going to put in for this Manning's N. And then the culvert, the channel invert elevation, that is, what is the elevation of the river where it matches up to where the culvert exits. And so the river is at 299.95. That's the elevation of the tailwater where it matches the culvert. So 299.95. Okay, if you click View, what it'll do is it'll calculate a rating curve. And this basically tells you what flow rate is going to cause what water depth in the channel downstream. So for instance, you can see that this river, if we wanted to get 25 cubic meters per second in the channel downstream, the depth of flow will be 3.8 meters. So that's kind of a nice calculator. But that's just telling you this rating curve so far is just for the river downstream of the culvert. We haven't told it anything about the culvert itself yet. Okay, so I'm going to close that. Now, the roadway data. The roadway station is 5 plus 3, 5. So that's just, it's basically, if you wanted to define where on your project this culvert crossing is, this first roadway station is really just a label. It doesn't factor into the calculations. 535. Okay, crest length is if the water flows over the road, how long is the crest? So 5 meters because it's rectangular. If the water's going over the top, 5 meters. It would be, you'd have to calculate it a little bit differently if it was trapezoidal. Like if it was trapezoidal, then the crest length would be this top distance. But for us, it's the bottom and the top are the same length because it's a rectangular channel. Crest elevation, here from this view, we see it's 307. If the water's flowing over the road, it does that beginning at 307 meters. So 307. It's paved on top, and the width of the road is 20 meters. I get that from this because it's basically about as long as the culvert itself. So if there's overtopping, it's going to use this information to know basically how much does the road itself slow down the flow. Okay, now I'm going to start putting in the culvert details. It's a circular concrete culvert, and the diameter of the pipe we want to check is 600 millimeters. Okay, so 600 millimeter diameter. Now, we don't have any details about like the embedment depth or the inlet configuration or if there's an inlet depression, so we're just going to leave all of these other details empty. And so the default assumption is that it's like a projected pipe that isn't mitered, it doesn't have a head wall, or I guess the default here is it's saying it's a square edge head wall. That's fine. We just won't change anything. I think you'll notice when you do the homework that if you do make adjustments to this, the effects are pretty subtle. Okay, now it needs to know how long is the pipe and what is the slope of the pipe. So the inlet station of the pipe, we get from here 100 and the outlet is 120. Okay, so inlet station 100. The inlet elevation, remember, was 300 meters. That's the elevation of the pipe. The outlet station was at 120. And the outlet elevation is 299.95. Now with that, now that I put in the elevation and the length of the pipe, it's calculated the slope for me. And you'll notice that the culvert slope is the same as the channel slope downstream, because the culvert itself is just sitting on the bottom of the channel. So it makes sense that it would have the same slope as the channel itself. Okay, so any questions so far? When you click on Analyze Crossing, you're going to get your answer. You got to do a little bit of thinking to know what it means, but what this tells us is that when the water level gets up to 307, it's only carrying 1.96 cubic meters per second through the pipe. So the original question was, can you get 25 cubic meters per second through that pipe? And the answer is absolutely not, and it's not even close. You're only getting like 2 cubic meters per second through the pipe before overtopping occurs. So this pipe is wildly undersized if we really do need to convey 25 cubic meters per second under this road without overtopping. So then if you wanted to go into iteration, the nice thing about the program is that then what you can do is you can say, all right, well, if 600 millimeters isn't good enough, what about 1200 millimeters? And analyze it again. And so you'll see now you've got 7.65 going through the pipe when overtopping begins. So that's still not big enough. And so then you can iterate another time. Just double click over here on the culvert and it'll bring up this data once again. What if we were to make the diameter 2,000 millimeters? Analyze crossing. We're getting pretty close now because we could convey 20.58 cubic meters per second as the water gets up to 307. So let's make it just a little bit bigger. What if we went with 2,500 millimeters? Analyze crossing. All right, so now what it says is to get 25 cubic meters per second, the water level's at 305.87. So our goal is to get 25 without the elevation of the water upstream going above 307, and it's doing that. In fact, when we have overtopping begin, it's at 28. So this culvert is big enough, and we maybe, depending on what's commercially available, could try to back it down from 2,500 a little bit lower as well. And that gives you the general overview of the program. You can get in there and start banging around, trying out the homework assignment. I think you can make some good progress on that. What we'll do on Thursday is take a look at another example. And so please have your computer. What I'll be doing on Thursday is more of just me not talking and circulating around and answering your questions and seeing if you are able to use the program okay. So bring your computers again on. Oh, today's Wednesday, Friday. I may have to, we've got a college meeting scheduled for Friday. We may end up having that as a recording, unfortunately. I'll let you know by email tomorrow. So Friday's class may be virtual, sadly. All right. Any questions before we go our separate ways? All right, that's it. Thanks a lot. I will see you next time.